Now, we're gonna do another problem, but I wanna revisit this one first. In that, what we had here, keep in mind, we had the change in the number of pounds of salt given some amount of time. In order to have that, we had 2 gallons per minute that was flowing in. That's the amount in. We had 3 pounds per gallon, that was the concentration. Over here, we had the amount, the portion of it that was flowing out. 2 pounds were going out of a total of 100. And then the X over here was the number of pounds that were in the tank, okay? And we wrote that X up on the top, of course, okay? Now, consider that was the case where the amount flowing out was the same as the amount flowing in. But what if that isn't the case that we had? So what if the amount of liquid in a tank was changing over time? We had constant volume before, but what if instead the amount was changing? So if we said we were flowing in 3 gallons per minute here, obviously the amount that's coming in is going to change, and if the amount that's coming in is going to change, we're not going to have 2 out of 100 gallons flowing out. After 3 gallons per minute, we had 2 gallons per minute going out, 3 gallons per minute coming in. So if we waited for 5 minutes, we'd have 105 gallons. If we waited for 10 minutes, we'd have 110 gallons. We have to take that into account. There is, how does that show up in this equation? So let's change, that was the first problem. Let's look at this and we say, okay, we're going to change things. 3 gallons per minute flowing in, and only 2 gallons per minute flowing out. Now, the amount, obviously the tank is going to rise up, the amount of liquid in the tank is going to go up, but also we need an additional term down here because the fraction of the tank that's going out is not as much as it was. 2 out of 100, we were always taking out 1/50th of the tank went out per minute, but the amount that's in the tank is going to go up. So flowing 2 gallons out per minute, when there's 100 gallons in the tank, it's 1/50 of the tank. By the time we get to 150 gallons, it's going to be, whatever that is, 1/75th of the tank. When we get to 200 gallons, it'll be 1/100th of the tank. So that's going to be a moving target. So with this arrangement here, we have to write a new equation, say, okay, dx dt, we're still talking about dx dt, and we can leave this as being a concentration of 3 pounds per gallon, that's fine. But if we have 3 gallons per minute in, and 3 pounds per gallon, again, from a units perspective, we've got pounds per minute, and 2 gallons per minute out, so 2 out of, how much do we have? Well, the amount that we have will be 100 plus whatever the difference is in how much flowing out and in. We said that there's 3 gallons coming in per minute, there's 2 gallons going out per minute, that's a net increase, right? If we said there's 2 gallons per minute coming in and 5 gallons per minute going out, that would be a net decrease. So this term could be a plus or a minus depending on which one of these is bigger. If this was 4 gallons per minute coming in and this was 2, we'd have a difference of 2. But right now, we just have a difference of 1 gallon per minute. That means every minute is going to increase the bottom by 1. So since our units here are in minutes, we're going to let that be T. And that is going to be how many gallons are going to be in the tank over a period of time. Now, we have to be a little bit careful here in thinking about this. 2 over 100, well, that was the number of pounds per the number of gallons in the tank. And now we're taking gallons and we're adding T to that. Well, not really. What we're doing is T, the amount of time is equal to the number of gallons. Because of the fact that there's 1 more gallon per minute. So as you multiply this by time, you'd have 3 gallons per minute minus 2 gallons per minute multiplied by number of minutes. That would be T, and you have 1 T. So T turns out to be the number of gallons. So it's not a units issue there. And then number of gallons. And then what we would have here is 2 gallons per minute out, and we have gallons, so we end up with just per minute going on here. We need the X, that's the amount of salt that was in there to start with, or that's the amount that's in there at a given amount of time. Okay. So our equation becomes that, which is a little bit different. Now we rewrite that equation, we say, well, what do we have? We have dx dt. Bring that over to this side so that we have 2x over 100 plus t. And I write the x outside here intentionally. And then that all equals, 3 times 3 is just 9. We can lose the units and simplify what the equation looks like again. Now, what do we have now? Well, again, Well, we have x prime here, we have a of t here, and just like before where we need an integrating factor in order to solve this, we need an integrating factor, but now this is what our integrating factor is coming from. We'll have e to the integral of 2 over 100 plus t and dt. So, whereas before it was a very simple integral to solve, this may be a little bit more difficult. We have to, think of a way that we can solve this. And of course, if we do this, what do we get? Well, we look at this and we say, well, it looks like dt over t. We got some extra constants, etc. But if we allow 100 plus t to be u, dt is equal to du. Du dt would be 1, and rearrange that. And therefore, we can rewrite this integrating factor as e to the, I'm going to pull the 2 outside the integral, and say, then what do I have? I've got du over u. Of course, it's natural log u. So I've got e to the 2 natural log of u. And going back to where we were, e to the 2 natural log of 100 plus t. And it really doesn't matter if I have parentheses or absolute values because t is time, it's positive, and so this is going to work. Okay, so that's our integrating factor. Now, when we have e to the something, and there's a natural log going on in there, well, we can bring this 2 up. So we've got more work to do with the integrating factor because e to the natural log of 100 plus t quantity squared, 2 transfers up there. E to the natural log goes away, and it turns out this is our integrating factor. So whereas we're kind of expecting an exponential in our integrating factor, it doesn't necessarily turn out to be what happens. Everything else continues on the same. We multiply by that integrating factor. So we're going to do that on both sides. And we get dx dt times 100 plus t quantity squared plus 100 plus t squared times 2x all over 100 plus t. I think, yes. And on the right hand side, 9 times 100 plus t quantity squared. And of course what happens here, say, well, that is what happens there, right? So now I look at this and I say, well, that's supposed to be related to, it's supposed to be this whole thing where it's the derivative of these 2 different things. It's a product. Is this derivative of a product? Well, if my product is x times 100 plus t quantity squared, and x is a function of t, I will hold the first, take the derivative of the second, plus hold the second, take the derivative of the first. And I see that is that, and that is that. So it still works, even though it's not an exponential. I have the same kind of result, which is this is the differential, or this is the derivative with respect to t of that product, x times 100 plus t quantity squared. And the right-hand side I can just write down. And again, I'm going to separate the variables now that I can, bring the t up here. My left-hand side, just the differential of this whole thing means that when I integrate that, it's just going to become x times 100 plus t quantity squared. And when I integrate the right-hand side, I look at that and I say, well, what do I have? I've got a 9 I can pull outside. And I've got u to a power where u would be 100 plus t, right? This t to a power, du would be equal to dt. So this is something to a power. I raise the power by 1 and divide by it. So when I integrate that, I get 100 plus t quantity to the third divided by 3. And then, of course, the obligatory plus c that always shows up here. And now I want to solve for x as a function of t. I'm going to divide through by 100 plus t squared. 100 plus t quantity squared. On the left-hand side, I'm going to get x. That's going to happen. On the right-hand side, I'm going to get 3 times 100 plus t, because the t squared is going to cancel most of that. And then I'm going to have plus c times 100 plus t, it's on the bottom, it's minus 2. Now, once again, if I want to find out what c is, I'm just checking to see if I actually filming this right side of the board here. If I want to find out what c is, I have to know more about this. How did it start? That again comes back to, well, what's going on at t equals 0? And if we said the same thing was going on at t equals 0 as before, which was that there was 50 pounds in the tank when we started, then we can use that here and say x at time 0 was 50. And at time 0, I have 3 times 100 plus 0 plus c times 100 to the minus 2. And now I want to solve that for c. It looks like this is minus 250 equals c over 100 squared. So it looks like c is negative 250 times 100 times another 100. Looks like that's c. So our total equation becomes x equals 3 times 100 plus t minus 2.5 million. And I'm going to write this instead of as a negative exponent right down the bottom.